Okay, so maybe it would have been a little bit less if we had actually put in a drop height of 0, resulting in a bounce height of 0. But we do notice that our calculator, it has a linear regression model. It doesn't necessarily have a direct variation model, forcing it into having an initial of 0. Nonetheless, okay, the more you squeeze a sealed syringe filled with air, the harder it gets to squeeze it farther. Okay, so like, let's suppose we just have, like a syringe and the cap, like you can't just, when you do the plunger, right, the cap is sealed. So as you do it, it gets harder and harder to push. It's very similar to having a bike pump, and if it's sealed and you're pressing down on the bike pump, it's very challenging to push it until you open it, and then you can push it and the air goes through, right? So the less volume you have, so you're pushing it so it's just a tiny amount of space in there, the higher the pressure will be. And the more volume, so you're not pressing it too much, it has a lot of room or a lot of space, the less pressure there will be. Okay, so these volumes and pressures in the syringe were recorded. So this data comes from this other book, both good books. But I really like this data set because it truly describes what's going on. Now, we're going to need to create a scatter plot for this data. So I went ahead and I put volume into list 1 and pressure into list 2. Okay, so let's label our let's label this. This is cubic centimeters, and this is in, what is that, atomic masses or something in pressure. Anyway, so we get our handy calculator, and we go to Stat, Edit, and what you'll notice here is in list 3, I have all of the volumes, and in list 4, I have all of these measurements of pressure. So I'm going to go ahead and go to Stat Plot, turn it on, and make sure I have, here's the scatter plot, list 3 and list 4, and then I'm going to go zoom 9. Ooh, there you go. That definitely has some curvature to it. So I see why it is in this section. Okay, so let's draw just a rough sketch of what's happening here. Right, it's going roughly something like that is what the scatter plot looks like. Label our axes. Got it. Does the graph have curvature? Yes. Yes, it does. That is the first thing I noticed, is that it wasn't a perfectly straight line. So, I mean, if it were linear, right, we would see this, but it is curving a little bit like our model suggests. Well, that would be inverse variation instead of direct variation. And remember, direct variation goes through the origin and has a line, okay? Whereas this definitely is not going through the origin, and it has some curvature. Okay, it says, fill in the chart. All right, so it wants us to multiply the volume times the pressure. Interesting. So, of course, you could do this one at a time. So 3 times 2.23, how much is that actually? 6.69. Because 2 times 3 is 6 and 3 times 3 is 9. Got it. But I actually am going to use the calculator to do this. I'm going to go to Stat, Edit, and a quick way to do this is I'm going to arrow over to L5 and hit Enter. And then you see this flashing at the bottom here. I'm going to put in L3 times L4 and hit enter. And you see all of these multiplications appear. List 3 times list 4 gives list 5 is what I just did. So, I mean, certainly you can do each one of these by hand, and that would be spectacular. But also sometimes it's nice to be able to use the calculator for some of these jobs, you know. That's what it was created for. It's nice to know what your calculator is capable of, and it's also nice to know what it is not capable of. Yes, then we can, and it's nice to know that somebody actually built the calculator. Okay, let's see. 13 times 0.56, that is 7.28. Okay, 14 times 5.2 is also 7.28, and this is 7.2. Okay, so we have all of these multiplied, and then it says find the mean average. Well, this is a great time to review this. Okay, remember that we find the averages by going stat, calculate the variable statistics, and we have list 5. You can see my fingerprints there, it's driving me nuts. Okay, and it looks like our average is about 7.26. Okay, so find the mean average of volume times the pressure. Well, that mean average, so was about 7.26. Write an equation describing the relationship between the volume and the pressure inside the sealed syringe. Okay, well, remember that we decided that we should use the inverse relationship, which has the model y equals k divided by x. And if we were to scale both sides of this up by x, that would be y times x, so scale up by x, and scale this up by x would just result in having k. So now I see, I get it. They were looking at multiplying this volume times this pressure in order to find this constant k. So this average is actually, so on average, when we multiply these two, we get this value of about 7.26. Some are a little bit below, some are a little bit above, but in general, they're right around 7.26. And this would be very similar to when we have a non-perfect linear relationship and we're finding the slope. It's going to perfectly match some, but not perfectly match others, because some of these data points will be on the curve and some of them will be a little bit off of the curve. Nonetheless, so we found our K, so we know that the pressure is modeled approximately by 7.26 divided by the volume, where P is the pressure and V is the volume. Yeah, so we have found our model. And I have a lot of remarks about this, actually. My first remark is that it actually took a lot of work to find K in this situation. So it takes work to find the constant K. And an inversely varying situation, or inverse variation model. Yeah, and your calculator doesn't do this regression, and that's why it took so much work. So let me show you precisely what I mean when I say that. So we took the trouble to find that on our own, because if I go to Stat, Calculate, it does a linear regression model, a quadratic regression, a cubic regression model, a quartic, so to the fourth power regression, another linear regression model. This is called a natural log model, an exponential regression, which we've used, a power regression, which we have not, logistic model, a sinusoidal model, and then a manual fit. So if we want to force a fit of a line on something. So it simply doesn't have the inverse variation model built into it. Basically, we have to, by doing this, we had to be smarter than the calculator. And luckily we are. So we multiplied and then we found the average, and that gave us our K in this situation. And that's only because we see that this is a proportion and we scale up. So solve this proportion, and that will let us find this variable K. Very similar to what we did in example, the first problem of example 2. Okay. More remarks is that we have several models now. We have a linear model where I write y equals mx plus b, but immediately I'm thinking it's the initial plus the constant change times x, and the linear model, I don't know, something like that. We also have a quadratic model, right? This model had curvature. Its model is ax squared plus bx plus c. And there were two shapes. Sometimes it increased then decreased, and sometimes it decreased then increased. Yes? Okay, but regardless, it had a rebound and no boundaries. The exponential model had the form y equals the initial times the constant multiplier to the x variable. And we had exponential growth. And we had exponential decay. Something of the sort. Where this had curvature, but it also went through 0. It had an initial value. And it had a boundary that it didn't cross. So it had one boundary and an initial value and a constant multiplier, or a consistent ratio. And then last, we have our inverse variation model. That is modeled by k over x. And it has a graph looking of these sorts, where it has two boundaries. It certainly has curvature, but now it has these two boundaries and no initial value whatsoever to speak of. So these other ones all had initial values that were incorporated into their model. I remember that the initial value is the c in the quadratic. The inverse variation does not have an initial value incorporated, because it would be like there was none in the direct variation, and here there is none incorporated in the inverse variation model. But it does have boundaries and it does have curvature. And then I also like to mention, I picked this example, this pressure and volume example, because I find it interesting. Your book talks about this relationship, or exploits this relationship of distance equals your speed times how long you've been traveling. So let's suppose you're running, how fast are you going times how long will tell you your total distance. And this obviously, well, this, maybe it's not so obvious, is a linear relationship that is a direct variation, because there's no initial value here, right? If you haven't run if your speed is 0, then your distance is 0. Okay, and then your book in this section said, okay, that's cool and dandy. if we scale both sides down by this rate, so if you take your distance, your total distance, and you divide it by your speed, then you find out how long you've been running. So if we scale down the distance by rate, we get the time. And now what you see is this relationship, or the fact that these are proportional to each other. And this one is called the direct variation relationship. And over here, this is called the inverse variation relationship. And so you're really just seeing it rewritten. Okay, there's no initial value to speak of here, but because it's 0. But you see the proportionality between the two. Okay, example 3, I actually found in a tech book. So I really loved it because it's an immediate application of this that we normally just don't think of very often. The force in pounds you must exert on a wrench handle of a given length to loosen a bolt is described by the equation F of L equals 720 L to the negative 1. Now this was, again, directly ripped from a tech book. Compute and interpret F of 12. So the first thing I want to mention is that this really is force, right? So I'm going to relabel this. Well, first this L to the negative 1 can be rewritten as division by L to the first power. Okay, so this is actually an inversely proportional situation, or an inverse variation situation. And I do like to rewrite this as force instead of F of L. So they use function notation, but really we could change that to force, and that's 720 divided by the length. So in this situation, they say F of 12, that means our length is 12. And so our force would be 60. Okay, and so how would we interpret this? Well, you need to exert this amount of force. So exert 60 pounds of force, okay, to a 12-inch wrench to loosen the bolt. Okay, so again, we see this inverse. So the longer the wrench, the less. So this is a torque situation, really. But I wanted you to see that it's really all over the place. Not to mention the fact that inverse variation is used a lot in sound, and so it has huge implications in the music industry. Okay, so as we kind of summarize what's going on here, okay, I do want to mention that we have looked at all 4 of these models in this class. In this particular model, inverse variation, we wrote and solved equations for scenarios that actually model inverse varying relationships. We also did it with direct variation because there's a relationship between inverse variation and direct variation. Yes, they're proportional relationships. Nonetheless, we have added on our 4th model and our last one for this particular class.